Good morning. I'll present you a test case where I'll show how structural optimization can be used in building design practice thanks to BIM. So if we look at the construction industry today, we see that there has been a wide gap in productivity improvements in manufacturing versus construction in the last 15 years, and this is due to industrialization. Basically, the construction industry productivity has stayed flat or turned negative, and traditional building methods have reached productivity improvement limits. So the construction industry needs to industrialize. The main challenges that it is facing today is to improve productivity, quality and sustainability, and reduce cost and waste. If we look at the design process, it is characterized by the fact that it is interdisciplinary. This is due to the fact that independent specialists come together to collaborate on a specific project, and it also characterized by heavy architectural constraints, for example, space and form. At the same time, it is ineffective and fragmented. It is characterized by numerous iterations and revisions, poor productivity, high risk, low profitability. This results in projects that are often over budget and behind schedule. If we look at collaboration, we see that it works quite good within each team, while there is a total lack of collaboration in between teams. The approach is usually manual, iterative, and trial and error. This implies long time for modeling and method customization, and it's a prohibitive practice. At the same time, design is based on rule of thumbs, and decisions taken are often based on previous experiences or intuition, but do not have a rigorous justification. So the construction industry is moving toward industrialization and standardization, and two are the main ways. One is modularization and off-site prefabrication, which is known as prefab, and the other one is information technology improvements. Basically, the design information needs to be structured appropriately for downstream application. And in this field, the solution has been identified into BIM. BIM stands for Building Information Modeling and consists in methods and tools to integrate, simplify, rationalize, and economize the entire design process. BIMs improves the flow of data through the building process and with current and future partners, starting from project concept and down to owner operations. BIMs provide a collaboration-based project backbone that enables centralized project and data management and the right information to be available to the right people at the right time. So basically, BIM is CAA for the construction industry. If we look at the development of BIM and how it is changed in the past years, we see that BIM approach started into the 1990s, and we are now here, where we can find transactable and interoperable data. This means that now BIM is ready for multi-objective automatic optimization. Currently, digital techniques that support the civil construction industry are being adopted most heavily in the United States, but the wave is starting in Europe and emerging countries like China. However, if we look at BIM and optimization together, we still see some main practical concerns which are related to optimization. Basically, there is a lack in theoretical and technical expertise, and many commercial tools seem to be targeted to the aerospace and automotive industry and to be inaccessible to designers who do not use them on a regular basis. At the same time, software licenses are often quite expensive, and the fact that design can change a lot in between revisions results in that optimization effort might become obsolete, so it basically turns into a waste of time. Now, if we look at cost in the construction industry for integrated design and construction, we basically see that it depends on the total weight of the construction. The cost has some main factors which are related to construction in terms of material, workshop activities, surface treatment, transport and mounting, and design services such as the actual design for workshop, construction supervision, and the final test. If we look at the construction components, we see that they are strongly related to detailed design, so they strongly depend on design services. So optimization turns into be looking for good compromises in between a light structure and low construction cost. So we tried to run this optimization on a real structural case of a steel building. So basically the objective was to see how rapid we could generate and evaluate a large number of design alternatives to better and faster explore the design space. And we also wanted to see the cost related to structural weight. The workflow built started from Autodesk Revit, from which we exported the structure, put it into robot structural analysis, connected to ModFrontier, checking stress rate, max displacement and total weight, and using these factors to optimize the performance of the steel building. Then we tried with different sections for each floor, changing beams and columns from a database of different profiles. So basically the optimization was run in between Robot and ModFrontier, and then the final optimal structure were exported again into the Autodesk Revit. This is the ModFrontier workflow. Here is where all the designs are reported, and we filter them just for feasible designs, which means that we put a constraint on stress. Then we did some more filtering in order to identify best solutions. We found the one that we chose as optimal, and we compared it to a manual solution. Now, if we look at the mass of the two configuration, which both pass structural test regarding low constraints, we see that there is a reduction in mass of 32%. But what does it mean in terms of cost? So if we look at the how costs are spread in between the different design aspects, we see that, and the actual construction, we see that the construction accounts for 87% of the total cost. This means that that's the one with the highest impact. And then we look at structural design and drawing for workshop, which is just 8%. So if we look at the savings, we can see that savings are quite important even for a very simple steel structure like a 5-floor building, which can be basically used as a parking. So we can conclude saying that the adoption of automated optimization in the building industry is a worthwhile endeavor, even if there are still important issues to be addressed. First of all, the design is paid basing looking at the cost. So there is no push for improving the design and making a lighter structure. Drivers can be seen as financial savings, which are mostly important for the one who has to pay, or in case of a tender, it's important to win the tender. In this regarding this aspect, we can say that a main driver can be seen in better exploration of the design space, especially in the early design stages. In fact, it is possible to discover unexpected feasible solution within defined constraints, like we did for the test case. However, there are still some issues that need to be addressed. First of all, companies have to be willing to change their long-standing work process. Moreover, initial investments are needed to develop capabilities before cost benefits are achieved. So, if we look at the scenarios of transition to optimization, we can say that there are two ways to move to optimization. One is faster and one is slower. Faster can be suitable for larger corporations with a larger turnover, highly skilled technician, and high adaptability, which is not the case of most companies in the construction industry. So construction industry can be seen in this case, so slower transition for smaller corporation, classical design and engineering approach, lower adaptability to complex software and working methods. So we can say that in this case, optimization can first be offered as a specialized service. In conclusion, we can say that opportunities will rise as this industry is just beginning its journey to support the full life cycle of construction assets using 3D tools, collaborative platform, and integrated project management. However, an adapted solution must be flexible enough to expand to meet today's and tomorrow's requirements. Thanks for your kind attention.